All right, so today our aim or objective is that we're going to determine the number of solutions to a system of equations, specifically graphically. So let's just break this down a little bit. Biggest piece here, a system or a system of equations. This is when we have more than one equation, with the same variables. So for the most part, we're just going to be working with equations that have x and y, but in general, a system of equations is when you have more than one equation and each equation has the same variables. Now, today we're going to be determining the number of solutions. So when I say number of solutions, I want you to think of two things. This means the number of intersection points, so the number of points where our graphs cross, and also the number of coordinates x, y that satisfy both equations. So we're going to be looking for how many times do our graphs cross, and then how many xy pairs will satisfy both of our equations. So we have three specific scenarios when we're trying to determine the number of solutions. We can either have one solution, we can have no solutions, or we can have infinite solutions. This is really similar to the work we did in the linear equations unit, just building on it. So if we take a look at this first system of equations, we can call this number 1. We have the equation y equals 1/2 x plus 2, and we have y equals negative x plus 5. So in order to determine the number of solutions on the graph, we just need to graph both equations. So let's start with this one. In this equation, our y-intercept is positive 2, so I can plot this point at positive 2. And then our slope, 1/2, tells me we're going to start at our y-intercept and go up 1 and right 2. This is the change in y over the change in x, so we can go up 1, right 2, up 1, right 2, up 1, right 2. And then in order to work backwards, the opposite of going up 1 and right 2 would be going down 1 and left 2. So now that we have these points, we can kind of see what our graph is going to look like. So now we can just connect them. Make sure we have the arrows going on both ways forever. So now we have this equation y equals 1/2 x plus 2, and let's graph the next one. So we have y equals negative x plus 5. So again, our y-intercept is positive 5. 1, 2, 3, 4, 5. Now this is the parts that could be a little bit tricky. I don't see a number in front of our variable, so I don't see a coefficient. We just have this negative sign. Whenever we don't have a coefficient, we assume it's a 1. So if it is a negative sign, we assume that our coefficient here is negative 1. So our slope is going to be negative 1 as well. A slope of negative 1 or negative 1 over 1 tells us we're going to go down 1, right 1, down 1, right 1, down 1, right 1. And so our graph is going to start to look like this. So again, this is the graph y equals 1/2 x plus 2, and then this one would be y equals negative x plus 5. Now our objective for today, we wanted to determine the number of solutions, or the number of intersection points. And if we look down on our graph, we can see that our intersection point is right here at the coordinate 2, 3. So this is our solution. This is the coordinate that is shared by both graphs. It's the coordinate that satisfies both equations. So we can say that this has one solution, and our solution is 2, 3. Now the big piece that I want to point out here is that when we had different slopes, this slope was 1/2, this slope was negative 1. This led to one solution. whenever we have different slopes, so this one, this line, and this line were going in a different direction, eventually they're going to cross. So every time we have a different slope, we're going to have one solution. Now, if we look at this next system, y equals 3x minus 2 and y equals 3x plus 1, we'll start off the same. We'll graph this equation first. Our slope, or our y-intercept right here is -2. So I'll plot that point, -1, -2. And then our slope of +3 tells us we're going to go up 3, 1, 2, 3, and right 1. Up 3, right 1, up 3, right 1. And working back the other way, rather than going up 3 and right 1, we can go down 3 and left 1. So now we can just connect our points to graph the equation y equals 3x minus 2. Cool, just to make this clear, I'm going to switch colors for the second equation. So we have y equals 3x plus 1. So same thing, we're going to plot our y-intercept at +1, and then use our slope of +3 to go up 3 over 1, up 3, right 1, and then we can work backwards just like we did before and go down 3, right and left 1, down 3, left 1. So this graph is going to start to look like this. Now, if we stop here and just look at the lines, we can see that they're called parallel lines. Let's just make sure we have this labeled, y equals 3x plus 1. Parallel means that they have the same slope. In this equation, the slope is 3. In this equation, the slope is 3. That means that between each point, both lines are going up 3, right 1, up 3, right 1. So they're never getting any closer to each other. We could think about this like putting pencils right on top of them. So our pencils are never going to get any closer to each other. They're never going to touch, even if we go this way or this way. So the big key point here is we have the same slope, but we also need to make sure that we remember we have a different y-intercept. We have a different starting point. This one's y-intercept is +1. This equation's y-intercept is -2. So we have a same slope and different y-intercept. This means we'll have no solution. These lines are never going to intersect. They're never going to cross. We also can never find a coordinate xy that'll satisfy both equations. If there's a point on this line, it's not going to be on this line. If there's a point on this line, it's never going to also be on that line. Alright, so far we have one solution when we have different slopes. We have no solution, we have the same slope and a different y-intercept. Now let's check out the last one. So just like we've done for the last two, we're going to start by plotting our y-intercept and using our slope to draw the rest of their line. So the y-intercept here is +2, and then our slope is also +2, telling us we're going to go up 2, right 1, up 2, right 1, up 2, right 1. And we can work backwards, go down 2, left 1, down 2, left 1, down 2, left 1. So the line's going to start to look like this. We can connect our points. Great. So this is the equation y equals 2x plus 2. Now let's do the same thing for the second equation. So our y-intercept here is +2. Now our slope, the slope is 4/2. This tells us we're going to go up 4, 1, 2, 3, 4, and right 2. So if we go up 4, right 2, that means we go down 4 and left 2. Now, what you might notice is that when we start to connect these points, we're staying right on top of that other line that we drew. The reason here is that 4/2, or 4 divided by 2, is the same as 2/1. So really these equations have the same y-intercept and the same slope. Now, we only really see one line here. They're both right on top of each other. And And that's because when we have the same slope and the same y-intercept, we have infinite solutions. And by infinite solutions, I mean that these two lines intersect at every single point. They're exactly the same line, and no matter what value we pick, we can pick any point on this line. It's going to satisfy both equations. So if you put the point 0, 2 into these equations, you'd get the same thing on both sides. If we put the point 2, 6 into both equations, it would satisfy both equations. If we picked the point -2, -2, it would still satisfy both equations. We can pick any point on this line and it'll satisfy both equations because it's on both lines. So again, we have one solution when we have different slopes. We have no solution when we have the same slope and different y-intercept. And we have infinite solutions when we have the same slope and the same y-intercept. Hopefully this helped. Make sure that you're using these strategies on the test. Think about the different slopes, same slope, different y-intercept, same slope, same y-intercept, and how many points that they will touch.